Hello all. In today's video, we'll discuss for the given system how to determine the gain value for the system to be stable, and we'll find out the k value for the marginally stable system. Here the term k, it represents the system gain value. So for in this example, so the characteristic equation of the system it is given. For this given system, feedback control system. For this feedback control system, we have to find out the range of k for the system to be stable and find out the range of value of k for the system to be marginally stable. Then find out the frequency of sustained oscillations. So how do we have to do it? First we have to form the Routh array for the given characteristics. So from the previous videos, we know how to frame the Routh array. The same procedure we are framing the Routh array. After framing the Routh array, we have to examine the first column elements. Here the last value is constant k. So in this Routh array, we have to replace that value as it is k. So proceed the complete Routh array in terms of k. So that is what here I have done it. So after this, let us do the first subdivision. In the first subdivision, we have to find out the range of k for the system to be stable. For the system to be stable, the constraint what it is, all the first column elements of Routh array must have the same sign. So here this is positive, here this is positive. That means all the other elements also in the first column of Routh array must be positive. So this is 71 by 5 positive. So here the term it is in terms of k. So S1 row, from the S1 row to be positive, so this value must be greater than 0. So 284 minus 25k by 71 by 5 greater than 0. So this only the numerator 284 minus 25k is greater than 0. From this k value it is k is less than 11.36. So this is from s to the power 1 row. Now with the same constraint, s to the power 0 row also must be positive. So the k value should be greater than 0 for the system to be stable. So here we got two values for k. One it is k is greater than 0. The other one k is less than 11.6. From here, we are deriving the k range. K lies between 0 to 11.36. Now, for the system to be, second subdivision, for the system to be marginally stable, when do we get the marginally stable condition? Whenever we get auxiliary equation, and only in that case, whether the system is stable or marginally stable condition. So, from the auxiliary equation, we will derive the roots. From the roots, if we get one pair of complex roots, if it lies on the imaginary axis, then the system it is marginally stable. So for that first, we have to get the row of zeros. So this row cannot be row of zeros because here we have values. S cube row also cannot be row of zeros. Here we have values. The same way, S square row, here 71 by 5 is it, here k can be 0. But here as per this constraint, k should be greater than 0. So this row also cannot be row of zeros. So there is, and first row and last row, these two rows cannot become row of zeros. So only there is a possibility of this row can become row of zeros. S to the power 1 row can become row of zeros. So when s to the power 1 row, when it becomes row of zeros, then auxiliary equation how do we get? Auxiliary equation we will get it from the row which it is just above the row from row of zeros. From here I will get auxiliary equation. So A of s it is 71 by 5 s square plus k marginal, which is equivalent to 0. Here I have to substitute k value as k marginal, because when I substitute k marginal value here, this row it becomes row of zeros. If you put k here as k marginal, and if you substitute 11.36 over here, this term completely it becomes 0. This term it becomes 0. Then this row will become row of zeros. Once if this is row of zeros, from here we will get auxiliary equation. So that is what here I have done. So when I write auxiliary equation over here, k should be replaced by k marginal value. So k it is now, k marginal is 11.36. So here this is the quadratic equation. So we can derive the roots. The roots are plus or minus j 0.894. Now the third subdivision, determine the frequency of sustained oscillation. So marginally stable, whenever the system it is marginally stable, the output curve, this is frequency, this is output, V0. So the output will be a sustained oscillation. So this will be the sustained oscillations. Whenever the system is marginally stable, we'll get sustained oscillation. So here the frequency throughout the frequency of this system will be always same. So that frequency only they are asking us to find out. So that frequency, how do we get it? Here the S roots we got it from the auxiliary equation. Here what is S value? S it is sigma plus j omega. So here the real part value it is 0. So I can equate this j 0.894 with j omega, where omega value it is equivalent to 0.894 radian per second. So this is how we need to find out for the system gain values for the system to be stable and for the system to be marginally stable, and frequency of the sustained oscillations. Now let us discuss about relative stability analysis. The relative stability can be specified by requiring that all the roots of the characteristic equation be more negative than a certain value. That is, all the roots must lie to the left of that line. All the roots must lie left of that line. S is equivalent to minus S1, where S is equivalent to minus x1, where s1 is greater than 0. The characteristic equation of the system under study is then modified by shifting the origin of the S-plane to S is equivalent to minus Z1 by the substitution S is equivalent to Z minus S1. If the new, by substituting S is equivalent to Z minus S1, we are obtaining the new characteristic equation. If the new characteristic equation in Z satisfies the Routh criterion, it implies that all the roots of the original characteristic equation are more negative than S is equivalent to minus sigma 1. Now, with this relative stability concept, we will see one example. So, S cube plus 7s square plus 25s plus 39, which is equivalent to 0. Let us check if all the roots of this equation have real parts more negative than minus 1. Here for this example, this term I have taken as minus 1. This term it is 0. So the S-plane it lies at 0, 0 real axis. This new plane where it is Z-plane, it is shifted to minus 1. Now I have to check for the given system whether all the roots are lying on the left hand side of where more negative than minus 1, left of this new axis. That is what we have to determine. Relative to this axis, whether the system it is stable or not. That is the check what we are going to do. So solution for this example it is shift the origin to S is minus 1. S is minus 1 because in the given example it is told that we have to check for this given equation whether all the real parts more negative than minus 1 or not. So S is equivalent to Z minus 1. So this is a substitution what we have to do it in the characteristic equation. So by substituting this, obtain the characteristic equation in terms of Z. So the new characteristic equation will be Z cube plus 4Z square plus 14Z plus 20, which is equivalent to 0. Now form the Routh array for this obtain new characteristic equation. So this is the Routh array what I have obtained. So in this Routh array, let us examine the first column elements for the stability. Here all the first column elements are positive. So the given system it is stable. So stable with respect to what? That we have to now tell. So now all the roots of the original characteristic equation, all the roots of the original characteristic equation in S domain lie to the left of S is equivalent to minus 1. Or another way how we can tell it is, as the signs of the all elements of the first column of the Routh array are positive, the roots of the characteristic equation in Z plane. The roots of the characteristic equation in Z plane lies in the left half of the Z plane, which it implies that all the roots of the original characteristic equation in S domain lie to the left half of S is equivalent to minus 1. This is relative stability. Let us see one more example on relative stability. So here the characteristic equation, it is given for a feedback control system. So for this given system we have to find the range of k is system gain for all the roots to lie to the left of S is minus 1. So the new axis Z it is placed at where S is equivalent to minus 1, left to that new axis whether the given system it is stable or not. That is what the check what we need to do it. So in the given characteristic equation, what do we have to substitute? Where S is equivalent to Z minus 1. S value is Z of whatever the value it's given, same thing we need to put it. S is Z minus 1. So this substitution we have to do it in the given characteristic equation. So S is Z minus 1 the whole cube plus 5 is Z minus 1 the whole square plus 12 into Z minus 1 plus k which is equivalent to 0. Now by substituting S is Z minus 1, we will obtain the new characteristic equation in terms of Z. So after obtaining the new characteristic equation in terms of Z, form the Routh array for this newly obtained characteristic equation. This is how we form the new characteristic equation. 1, 5, 1, 5, 2, k minus 8. Its constant value is k minus 8. 2, k minus 8. 2 into 5 minus 1 into k minus 8 divided by 2. The same way proceed the Routh array and complete the Routh array. Now, for the system to be stable, all the first column elements must have the same sign. This is positive, positive. This also supposed to be positive, positive. So, by considering that constraint, from the z to the power 1 row, this value must be positive. So, this should be greater than 0. 18 minus k by 2, it should be greater than 0. So, from this k value, this equation is an inequality equation. From this we are finding the k value must be less than 18. This is from z to the power 1 row. For the system to be stable, z to the power 0 row also must be positive. So, k minus 8 value from z to the power 0 row, it should be greater than 0 for the system to be stable. So, from here k value is greater than 0. So, here we got two different conditions for k value. One it is k is greater than 8. The other value is k is less than 18. By combining these two conditions, we obtain the k range is 8 to 18. Now, from this how we can conclude it. Hence, for all the roots of the given characteristic equation to lie to the left of S is minus 1, the condition is that k lies between 8 to 18.